Hi everyone, welcome to my lecture on resonance and formal charge. So today we're going to be talking about resonance and introducing a few concepts about how we describe or formalize the movement of electrons both in resonance structures and in reactions. So there are two types of arrows that I'm going to use in the presentation today. One of them is this curved arrow that we use for what we colloquially call pushing electrons. It's technically called the curved arrow formalism, but it'll make more sense, I think, once you see it in context. But you'll note that you have a pair of electrons, and then you have the tail of the arrow, and it's pointing to something. The other type of arrow that's going to be that I'm going to talk about today is this resonance arrow. You can see that it has two heads, one on each end. So the model molecule I'm going to use is that of benzene. Now you may recall from class and from the readings from Chem 1, Chem 2, benzene is this special molecule. It has these 6 carbon atoms in a ring and has these alternating double and single bonds. And what was discovered about benzene is even though normally we expect, say, in ethane and ethylene that single bonds are longer than double bonds, what's observed is that all of these bonds are the exact same length. And the reason for that is there is one other resonance structure for benzene, and that is how we can sort of explain or show these that these aren't actual double bonds; these aren't actual single bonds. So when we draw a resonance structure, the first thing to do is to remember that all of the atoms go in the exact same place. So I'm going to start by putting in all the carbons and the hydrogens, and then in resonance structures, sigma bonds never move. So I'm going to put in my sigma bonds here. In resonance structure, what can move are pi bonds and lone pairs. We don't have any lone pairs in this structure, but we do have some pi bonds. So where there's a pi bond here, no pi bond here, what I'm going to do for this resonance structure is essentially move the pi bonds to between the atoms where they weren't before. Now, since these are two resonance structures of benzene, I'm going to put a resonance arrow between them, and often we put brackets around the two structures, although I sometimes don't bother to do that. All right, so there is a pair of resonance structures. They have, again, the same exact atoms in the same exact orientation, and I have not changed any sigma bonds. What's moved in this structure is pi bonds, and I'll do another example where you'll see lone pairs being moved around as well. Now, what we also like to ask as chemists, as organic chemists, is, okay, how did these electrons get from here, say, to here? And this is where the curved arrow formalism, the electron pushing arrows, comes in. So this pi bond in the left resonance structure is right there. The right resonance structure is right there. And so what I'm going to do, take my pen here and draw an arrow. So I'm going to start at the initial pi bond and draw an arrow pointing to the nucleus where it's moving to. So again, you see the arrow starts at the pi bond and it points to the nucleus where this is headed to. Now, if this were the only arrow, then this carbon would wind up with 5 bonds. We can't do that, so I'm going to draw these arrows in for the other pi bonds to show their motion around benzene as well. So again, start at the pi bond, point to the nucleus. Start at the pi bond, point to the nucleus. So there you have it. There is our benzene, our resonance structure, our arrows showing how the pi bonds move to get from the one on the left to the one on the right. Good practice would be for you to draw this and then draw arrows showing how to get from the one on the right to the one on the left. All right, so the next molecule I want to talk about is acetone. The first thing that you should notice is where are the lone pairs on oxygen. Sometimes we organic chemists neglect to draw our lone pairs, but for resonance structures you always want to show your lone pairs because sometimes they move. So you always want to be able to count for these, see what's got a full octet, that sort of thing. Now I know I'm going to draw a resonance structure, so I'll go ahead and put in my resonance arrow. And then, like I said, in resonance structures, the atoms don't move and the sigma bonds don't move. So I'm going to draw in those. All right, so I've got my carbon atoms, I got my oxygen. The resonance structure for acetone looks like this. Well, what's happened? Let's first ask that. All right, well now we have a third set of lone pairs on oxygen, and this pi bond between the carbon oxygen and the carbonyl pi bond has moved. Let's draw that in. So this pi bond of electrons went from being a pi bond, start the arrow there, and it moved up onto the oxygen. So that's the arrow pushing formalism of that. Now this one looks a little bit funny. Why is that? Well, the carbon here doesn't have a full octet. It's only got 3 bonds. And surprisingly enough, that's okay. It's a minor resonance structure, and it's okay to have resonance structures where carbons don't have full octets. Nitrogens, oxygens, halogens always have to have full octets. Carbons, it's actually okay sometimes if they don't. What you do have to do now is show formal charge. So in this case, carbon has a plus formal charge, oxygen has a minus formal charge. All right, so now suddenly I've just thrown this concept of formal charge at you. What does this mean? So formal charge is this, is equal to the number of valence electrons of an atom minus the number of owned electrons. And for owned electrons, a bond counts as 1 and a lone pair counts as 2. So if we're talking about this carbon right here, carbon, it's got 6 electrons total. 2 of them are on the inner 1s orbital, so they're not valence electrons. Carbon has 4 valence electrons. It's in the 4th column of the periodic table. So carbon has 4 valence electrons. In this case here, it's got 1, 2, 3 bonds to it. Each bond counts as 1, so we subtract 3 from 4. We get 1, positive 1, so carbon has a plus formal charge. Oxygen, on the other hand, it's in the 6th column of the periodic table. It's got 8 total electrons. It has 6 valence electrons. In this case, it's got a lone pair, a lone pair, a lone pair, so 2, 4, 6, and 1 more from the bond is 7. So remember, lone pairs are 2, bonds are 1, 2, 4, 6, 7. So we subtract 7, and hence oxygen has a -1 formal charge. One last thing to say about formal charge is to note that negative plus positive equals 0, so you're never going to change the total formal charge in a molecule. So this starts as a neutral molecule. We're always going to have negatives and positives canceling each other out. If we started with a cation, we would always wind up with formal charges summing up to +1. Anion sums up to -1. We'll talk more about this in class next week. We'll talk about why this resonance structure is more important or more real, shall we say, than this resonance structure. And I'll show you some of the patterns when you start, so you can start to recognize you don't always have to do this longhand calculation to figure out the formal charge of an atom. So, see you next week.